Welcome to The Explainer. I'm honestly so excited you're here today because we're going to unlock one of the most fascinating secrets behind medical data. We're talking about population health statistics. Now, I know that sounds heavy, but unlocking complex health data really just comes down to mastering one simple, incredibly powerful concept. It's something I like to call denominator discipline. Trust me, if you can master the denominator, you will be able to see right through the noise of literally any medical headline. To kick things off, let's think about a paradox. Why would a groundbreaking new treatment, one that literally extends patients' lives, actually make the overall disease statistics look worse? I mean, it sounds completely backwards, right? If a drug is keeping people alive longer, shouldn't the numbers look better? Just keep that epidemiological mystery in the back of your mind for now, because solving it is our main goal today. Act 1, the burden versus the risk. Okay, let's dive right in. To resolve our mystery, we really need to pull apart two terms that get confused all the time. First up is prevalence. Simply put, prevalence is the total proportion of a population that possesses a disease either at a single point in time or over a specific period. You can think of it like taking a giant snapshot of the total burden of a disease in a population. If we take a picture of a city right this exact second, how many people in that picture have the condition? That is your prevalence. It includes absolutely everyone, people diagnosed 10 years ago and people who were just diagnosed yesterday. This sets up the first half of our mathematical relationship. Now, incidence is a totally different concept. Incidence doesn't care at all about the people who already have the disease. It only captures the rate of completely new cases occurring within a specific population over a defined time frame. And this is exactly where our denominator discipline has to kick in. To calculate incidence correctly, your denominator must strictly include only the individuals who are genuinely at risk at the start of the period. That means anyone who already has the condition or is maybe immune to it absolutely must be completely excluded from the bottom of your fraction. So let's put them head to head. This perfectly illustrates why denominator discipline is so crucial. Look at the direct contrast here. Incidence is your new cases divided strictly by the at-risk population. Prevalence is your total cases divided broadly by the total population. Think of it this way. Incidence tells you your actual risk of catching something today, while prevalence tells you how widespread the disease already is out in the real world. So how do these two connect? Well, they're linked through a really simple mathematical formula. Prevalence is roughly equal to the incidence rate multiplied by the average duration of the disease. In other words, the total burden equals the rate of new cases flowing into the population multiplied by how long those cases actually stick around. And this, my friends, gives us the exact key we need to solve that paradox from the beginning of our explainer. The really crucial point here is understanding how different medical interventions manipulate those specific variables. Take a new vaccine, for instance. A vaccine alters the system by decreasing incidence. Fewer new people are getting sick, right? And because incidence drops, prevalence subsequently drops too. Now, what about a cure? A new cure will rapidly decrease prevalence because people are getting better, but it actually leaves the baseline incidence rate completely unchanged. People might still catch it, but they're cured quickly. But here's the kicker. What happens when a drug extends a patient's lifespan but doesn't actually cure them? Well, a super common mistake, especially on medical exams, is assuming that a life-extending drug reduces the overall disease burden. It doesn't. Because the treatment extends the overall duration of a chronic illness without providing a full cure, it actually causes the population prevalence to rise. And boom, there is the answer to our paradox. Extending life means patients live longer with the disease, which means the total number of people currently living with it, that prevalence burden, actually goes up. Act 2, the mortality matrix. All right, we've talked a lot about how people get sick, but now we need to explore how we measure death in a population. When evaluating population mortality, clinicians have to separate another pair of easily confused metrics. And yes, this requires some serious denominator discipline. Let's contrast the case fatality rate with the crude mortality rate. The case fatality rate measures explicit virulence, basically how deadly a specific condition is. It isolates a very strict denominator. You calculate it by dividing the total number of deaths caused by that specific disease by the exact number of individuals diagnosed with it. On the flip side, the crude mortality rate reflects the absolute toll of all deaths across an entire geographical area. Its denominator is broad and massive. You calculate it by dividing the total number of deaths from every single cause by the total mid-year population. To really wrap our heads around this, let's look at some extremes. Take rabies, for example. If you get rabies, the case fatality rate is near 100%. It is explicitly incredibly virulent. But because it's such an exceptionally rare condition, its actual impact on the crude mortality rate of a large nation is completely negligible. Now, on the other extreme, think about a highly contagious but relatively mild respiratory virus. That virus is going to demonstrate a very low case fatality rate because most people survive it. However, because it infects millions and millions of people, it can generate a massive absolute number of deaths. That widespread transmission drives the crude mortality rate way up, despite the virus itself being mild. Act 3, the closed town case study. I think the best way to really get this is to practice it. So I want you to calculate these concepts with me right now, using a hypothetical closed town. We'll track the data over a 12-month period. Okay, on January 1st, we start with a stable population of exactly 10,000 residents. Now, at the start of the year, 1,000 of those residents already carry a chronic autoimmune condition. Over the next 12 months, an additional 200 individuals are newly diagnosed with this illness. Fast forward to the end of the year, December 31st. 50 of those newly diagnosed patients and 50 of the pre-existing patients unfortunately pass away directly from the autoimmune condition. Meanwhile, 100 otherwise healthy residents die from unrelated accidental trauma. Okay, hold those numbers in your head because we're going to do a little live math. Let's start with the incidence rate. And remember our denominator discipline here. We know we have 200 new cases, but what is our denominator? Well, we started with 10,000 people, but 1,000 of them already had the disease, right? So they aren't at risk of catching it anew. That means to calculate the incidence rate, we divide the 200 new cases strictly by the 9,000 residents who actually started the year healthy and at risk. And that yields an incidence of 2.22%. Next up, let's find the case fatality rate for this autoimmune condition. We take the 100 total deaths caused specifically by the illness. Then we divide that by the exact total number of individuals who actually had the disease during that year. That's our 1,000 pre-existing cases plus our 200 new cases, giving us a strict denominator totaling 1,200. So 100 divided by 1,200 gives us a case fatality rate of 8.33%. Finally, let's figure out the crude mortality rate. This is the absolute toll for our town. We combine the 100 disease deaths and the 100 accidental deaths, giving us 200 total deaths. Then we divide that broad numerator by the broad initial population of 10,000 residents. That yields a crude mortality rate of exactly 2.00%. See how identifying the proper denominator literally changes everything? Act 4, the ultimate confounder. Now there is one massive trap waiting for us when evaluating population metrics, and it's the most critical execution point on medical boards: adjusting for age distribution. Imagine we're doing a baseline comparison of crude mortality rates between a retirement community down in Florida and a lively university town in Texas. If you just look at the crude mortality rate, Florida's going to look incredibly dangerous. A lot more people are dying per capita. But is the healthcare actually worse in Florida? Well, no. Comparing them directly creates a massive distortion simply due to the uneven concentration of elderly individuals. Age is completely confounding our data. So how do investigators make a scientifically valid comparison about health outcomes between two totally distinct populations? They use something called age standardization. This is a mathematical normalization process. Basically, by tweaking the math so the population's age distributions match, it eliminates age as a massive confounding variable. It levels the playing field, allowing for a pure evaluation of the underlying epidemiological risk factors. So you can finally see what's actually going on. Which brings us to the end of our explainer. I want to leave you with one final provocative question. Are you checking the true denominators behind the medical headlines you read? The next time you see a news report panicking that a disease is surging, just stop and ask yourself, is the true incidence actually rising? Or is a new drug just keeping people alive longer, naturally pushing up the prevalence? The power to understand the absolute truth of health data is literally right there at the bottom of the fraction. Thanks so much for joining me today. Keep practicing that denominator discipline, and as always, stay curious.